This is part 2 of a series about using simple continued fractions to decompose Pythagorean primes. We'll outline the process and work 2 examples. Let's get started. The process has 3 steps. We'll write them down shortly, but let's remind ourselves of the problem statement. We are given a Pythagorean prime n sub p, and we want to find the 2 integers a and b that satisfy a squared plus b squared equals c squared equals n sub p. Also, before we begin, I wish to acknowledge this paper by John Brillhart in 1972. The process we're about to see is based on this paper. The citation is given in the description. In step 1, we find the integer x such that x is between 0 and half of n sub p, and also such that x squared plus 1 is divisible by n sub p. Another way of saying this is we find x such that x squared is congruent to negative 1 mod n sub p. For primes of reasonable size, you can find x using brute force. With a short routine or even a spreadsheet, you can check the values in this range and find the one that satisfies this condition. The author of the paper I just mentioned provided a different approach. Here it is, I'll let you read it. It is more direct and seems a lot more elegant than brute force, but I haven't had an occasion to learn the concepts in this paragraph. I have to admit, when I read it, it practically feels like reading a foreign language. Feel free to use this method, but I just use brute force. In the future, maybe I'll learn this other method and do a video on it. Step 2. Begin expanding n sub p over x into a simple continued fraction. While you are doing this, keep an eye on the remainder. When a remainder is less than the square root of n sub p, you can stop. Let's pull up a blackboard and explain what is meant by a remainder. We have the remainders when we expand numbers into simple continued fractions. You just need to know where to look. In another video about expanding numbers into simple continued fractions, we used a table like this, with columns for k, alpha, a, and 1 over alpha sub k plus 1. In each row, k is just an index or subscript. Alpha is a number that we break up into its integer and remaining fraction. A is the integer part, and 1 over alpha sub k plus 1 is the remaining fraction. We also had a column for alpha sub k plus 1, but it is just the reciprocal of the previous column. We won't fill this one in during this video. Please see the other video if necessary, so you'll understand each term here. Let's talk about the remainders. The remainder in each row is the numerator of the term in this column, the column with 1 over alpha sub k plus 1. Let's suppose we are expanding 170 over 39. That becomes the alpha in the first row when k equals 0. The integer part of 170 over 39 is 4, and the remaining fraction is 14 over 39. We have a remaining fraction now, but what is the remainder? Do you know what it is? It is 14. If you divide 39 into 170, it is 4 remainder 14. The remainder shows up as the numerator in 1 over alpha sub k plus 1. As we said before, we won't fill in this column, but let's do one more row. K is 1, and alpha is the reciprocal of 1 over alpha sub k plus 1 in the first row. It's 39 over 14. The integer part a is 2, and the remaining fraction is 11 over 14. The remainder, though, is the numerator of this. It is 11. If you divide 14 into 39, it is 2 remainder 11. Let's add this information to step 2. The remainder is the numerator of 1 over alpha sub k plus 1. In step 3, we write the solution. If the remainder in the first row equaled 1, then a and b are 1 and x. Otherwise, if the remainder in the first row was greater than 1, then a and b are the first 2 remainders that are less than the square root of n sub p. So you have to add one more row to the expansion you did in step 2. These step-by-step processes might sound complicated, but give it a try. This isn't so bad. Now let's do some examples. In our first example, the Pythagorean prime n sub p is 173,189. We'll also need the square root of this, so we note that it is about 416.2. For the first step, I wrote a short routine and found that x equals 77,823. You can check for yourself that if you square it and add 1, the result is divisible by n sub p. In step 2, we start expanding 173,189 over 77,823 into a simple continued fraction. Here's the table I mentioned. Can you do the first row yourself? Stop the video and try to do it. Here it is. Now we check if this value, the remainder, is less than the square root of n sub p. It is not, so we have to do at least one more row. Here is the next row for k equals 1. This remainder is also not less than the square root of n sub p, so we keep going. When k equals 2, the assessment is the same. the remainder is not less than the square root of n sub p, so we keep going. When k equals 3, same thing. Notice the remainders, these numerators, are getting smaller and smaller in each row. And when we get to the row for k equals 4, the remainder is less than the square root of n sub p. This value, 385, is less than this one, 416.2. We could stop here, but in step 3, we'll need one more row, so let's just add it now. Here it is. In step 3, we just write the solution. The first remainder was greater than 1, so a and b are the first two remainders that are less than the square root of n sub p. A and b are 385 and 158. We can check that they satisfy the equation. The sum of their squares equals n sub p, so they satisfy the equation. We'll do one more example. This time the Pythagorean prime is 115,601, and its square root is just over 340. In step 1, we found x that satisfies the conditions is 340. In step 2, we start expanding 115,601 over 340 into its simple continued fraction. Here's our table. In the first row, for k equals 0, the integer part is 340 and the remainder is 1. 1 is less than the square root of n sub p, so we can stop. This time, we won't need another row in step 3, but I'll add it just for the sake of completeness. Here it is. On to step 3. The first remainder was 1, so a and b are 1 and x. And so for this example, a and b are 1 and 340. We can check to make sure that when we sum their squares, they add to n sub p. They do, so this a and b satisfy the equation. I realize this might seem complicated, but try to do some examples yourself. After you do this a few times, it starts to seem less complicated. In this video, we wrote down a process for using simple continued fractions to decompose Pythagorean primes, and we worked a couple of examples. That's all for now.